Hi, welcome back to the channel and video number 102. This is part 2 in a series on liquid-cooled aircraft engines. So if you haven't watched part 1 yet, that would probably be a good thing to do. And this one will concentrate more on practical considerations, design, layout, how things were built, the Meredith effect, how to lower drag. And hopefully you'll find this video interesting and informative. Let me know in the comments below. So this video will concentrate almost exclusively on belly ducts or ventrally mounted radiators, and it will have some details on my RV6A as well as Russell Sherwood's glass air that you've seen before, how we designed them, how we built them, and how they work. So why do we need these complicated ducts? Can't we just put the radiator on the front of the engine like in this Eggenfellner type installation? Yes, you can. It works. However, there's no chance to recover momentum. You have very high losses here. The air comes out much slower here behind the radiator. There's no chance of converging the flow. It has to pass by all these obstructions on the way out through the belly scoop here. So the advantage of having the radiator up front like this attached to the engine using the normal scoops is that it's easy. And packaging the coolant piping is definitely shorter. The engine's right here. We don't need to pipe it back to the belly. So that's why some people do this. However, it's not the most efficient way. And that's why this video, we're not just concerned about cooling, which is pretty easy. We're concerned about cooling with low drag, and we're just trying to illustrate how that's possible. So this is an example of what not to do for low drag. And this is an example of what to do for low drag. All of the aircraft you'll see on this video today will feature a variable geometry exit door from the radiator, and we'll explain why this is so important. So here's a chart from back in the 40s demonstrating why the variable geometry exit door on a radiator can cut drag. And on the left side here we've got indicated airspeed, miles per hour, and on the bottom here we've got exit door area in square feet. And you can see with the exit door closed, getting about 198 miles an hour, and with the exit door open, that drops off to about 193 miles an hour roughly. So we're seeing about a 5 mile an hour increase by closing the exit door. And on other World War II aircraft, and especially at higher speed, we see speeds increase 22 miles per hour by closing the rad exit door. It's pretty substantial. So if we design our radiator duct and radiator assembly properly, it may be possible to obtain thrust rather than drag from it. So this illustration just shows basically what that's about. We've got our radiator duct here, radiator here, inlet air coming in at velocity 1. The air is heated after the radiator here, and it exits at velocity 2. So if velocity 2 is less than velocity 1, you get drag. Obviously, if the air is coming out here slower than it did here, that's drag. If velocity 2 is more than velocity 1, if it's going faster as we exit it than it came in here, we obtain thrust. So if we're after low drag in our cooling system, the fundamentals of this are mass times momentum loss equals drag. So I instrumented my RV6A with temperature probes, static and pitot tubes in order to quantify the performance of the radiator. And you can see the temperature and pressure probe lines taped to the side of the aircraft here as I go up for a test flight. So at 110 knots with the exit door closed, we had an inlet pressure prior to the radiator of 6.5 inches of water, and the exit pressure was 5 inches. Coolant temp going into the rad was 70 degrees, and the air leaving the radiator was 60.3, so pretty efficient. And the exit velocity was 85 knots, so compared to the 110 knots here. And with the door fully open, we had a drop in pressure from 6.5 to 6, big drop in pressure at the exit side from 5 to 3. And we can see here the air temperature is quite a bit cooler. That's because we've got a lot more air flowing through there. But we can see here the big difference in air velocity at the exit of the duct. It's only 61 knots here, and it was 85 with the duct closed. And this is creating a lot more drag, obviously. So the result of the testing, pretty successful. Managed to get the exit velocity to 104.5% of the inlet velocity. Radiator effectiveness was 92%, and pressure recovery with the door closed was 84%. Here we have an illustration of the P51 cooling system, and it's the aircraft most often associated with the Meredith effect and perhaps getting thrust rather than drag from the cooling system. So here we can see the divergent duct, or the diffuser, and the air comes in here. Some of it split off through the oil cooler. The rest of it goes through the radiator, and the diffuser basically slows down the air from the entry as well as spreads it out over the entire radiator face, so we get air going through all the tubes and fins. And on the exit side we have a convergent duct, which speeds up the airflow, and we also have a variable geometry exit door, so we can open that at low air speeds, say on the ground for best ground cooling, also in the climb where we've got very high power, so very high heat, and relatively low airspeed. Then we can also close the duct further in cruise flight where we have very high mass flow and we don't need so much cooling. That has the added benefit of increasing the velocity at the exit even further. And here's a slightly different view or perspective of the duct. You can see the inlet here, the oil cooler, and these are separated by a wall. And here you can see the shape of the diffuser. It gets larger as you go aft and spreads out the airflow and slows it down prior to the entry into the radiator. And here you can see the convergent part of the duct as well as the variable geometry exit door. So I found this very interesting report online from 1942 on radiator ducts and diffuser design especially. So we can see from this chart from that 1942 study, they're comparing diffuser efficiencies over here with the effective opening angle of the diffuser. They plot it with no resistance or no radiator in the duct in these dotted lines here. You'll see that maximum efficiency or pressure recovery of the diffuser is at opening angles somewhere around 7 to 8 degrees. However, they tested it with simulated resistance grids, not radiators in this case. You can see that characteristic changed quite considerably when there's a resistance to flow. The opening angle of the diffuser is far less important, and we can see it's not radically altered, or you don't have a lot less efficiency until you reach probably around 30 degrees. The efficiency is pretty good here. So that's an important consideration in diffuser design. Obviously, when you get out to 40 to 60 degrees here, the efficiency of the diffuser drops off considerably, and you just don't want to do that. So there was lots of great information in this study, and you can find it online if you're more interested. However, to keep this short, I just wanted to go to their main conclusions here. And they're basically saying as long as the diffuser opening angles are less than 30 degrees and you've got some resistance from the radiators, diffuser losses were found to be pretty small. They're basically saying in the 0.3 here that the greater the resistance of flow in the radiator, the higher the diffuser efficiency. Or you could have a greater expansion angle for the same losses. So here we have a graphic depicting different diffuser shapes. Here's the low divergent angle one. You can see it goes from this area to this area over a longer length than this one. This is a high divergent angle one. You can see this is going from the inlet area to the radiator area over a much shorter length. And because of that, the airflow, especially in the corners, hits the radiator matrix here at a more obtuse angle, so there's more drag and possible separation here. On the low divergent angle duct, the air meets the radiator matrix at lower angles, so it doesn't have to turn as much, and usually that creates less momentum loss, less drag. So generally speaking, the low divergent angle duct is more efficient, and the high divergent angle duct is less efficient. So Russell and I both did some high capacity blower tests with our radiator ducts. You can see that over the next few frames here. And we ended up putting guide vanes in both of our radiator ducts. hoping to smooth out the airflow and stop the turbulence as the air turns upwards towards the top part of the radiator. Since the radiators we're using have very low flow restriction, we thought the guide vanes were important to get maximum performance with minimum turbulence and drag. And here's what Russell ended up with on his design. These next few frames show the layout on my RV6A. You notice where the radiator core is the only thing that's being touched by the air. The tanks are not touched by the air going through here. That's really important for low drag. The tanks just present a whole bunch of drag that you don't want. And here's the exit door on my radiator setup in the open position. And here's my finished duct shown in the inverted position. Here's the flange used to attach the radiator duct to the belly of the aircraft. Here's the routing of the coolant hoses so that they are not touched by the air at all. And you can see in my case that we didn't add very much frontal area with the scoop here. I used an aluminum splitter to keep the cowling air from impinging on the radiator inlet. Here's a drawing of Russell's radiator, which some people might find interesting. These next several frames show Russell's radiator duct under construction. And you can see how he was able to raise the radiator up into the airframe to reduce the frontal area with the composite aircraft. And this was something I wasn't able to do with the RV6. With the metal airplane, it was already completed. I was stuck with having to have the radiator below the belly skin entirely. And you can note in the next several frames here how the radiator is offset to the right on Russell's airplane. And that's to prevent, again, ingestion from the cowling air going into the radiator, which you definitely don't want. And here's some more views of my aircraft from the side and the front. And with the exit door open. And with the exit door closed. I just use a simple Bowden cable to actuate the exit door on my aircraft. And this is the locking control inside the cockpit to activate the door. So here we see another variation on the variable geometry exit door. And this is on Russell Sherwood's Glass Air. He uses a servo motor located up here and a push rod to control the aperture of the duct exit here. But in order to have any chance of reducing drag to a substantial degree or actually getting thrust, you must have a variable geometry exit door. There's no other way around it. You can't have good ground cooling and good climb cooling and lowest drag and cruise with a fixed outlet. It's impossible. Here's a couple photos of the electric actuator mechanism on Russell's Glass Air. Here's a couple more examples of electrically actuated rad doors. This one on a Thunder Mustang, and this one on a V8 powered Legend. Notice the emergency cable release on the right side in case the actuator freezes. So you might ask why we don't throttle the inlet as well as the outlet, or just the inlet on radiator scoops. Well, in the early days of the P51, the NA73 prototype, they did have a setup where they changed the inlet aperture, as you can see here, closed and open, as well as the exit door aperture. And indeed the Mustang 1 used something quite similar. However, further experimentation showed that there's very little loss with the fixed inlet, and just varying the outlet size to increase or decrease the flow and the exit speed. So the later Mustangs eliminated this rather complex inlet door setup here and just went with a variable exit door and kept the inlet aperture fixed. So here's a pretty good photo of the Mustang 1 inlet door. You can see it here, and the exit door is closed in this case. So the later P51s didn't have this at all, and they had a reshaped or revised inlet aperture here. So with regards to the water part of the radiator, I use 3/4 inch tubing to route the water supply on mine. That's more than adequate for this amount of horsepower. You can see the fairing on the upper right of the photo covering Russell's coolant tubes, which are 1 inch diameter. I thought I'd throw in 3 photos of a rather nicely done radiator setup on canard design. And this was done by the Clark Brothers Subaru powered. And another Subaru powered canard here. So here's a good shot of Voodoo, which is the fastest piston powered aircraft in the world. They have a completely revised radiator duct compared to the stock P51. They've eliminated the scupper or boundary layer splitter here to reduce frontal area. They've also increased the length of the whole duct right back to the tail wheel opening, and different radiators of course as well. So the length of the duct is quite important for lowest possible drag, and the exit door geometry is radically different from the stock P51 as well. You can notice how long the door is here. It's probably 3 times longer than the factory P51 door, and the nozzle is a different shape as well. No doubt the people who prepared Voodoo did a lot of experimentation here, finding the optimal shape and size of the radiator duct and so forth, in order to get the least amount of drag. It's very important when you're going speeds like this. And here we have a nice close-up shot of Voodoo's radiator inlet. You can see how different this is from a stock P51 here. And here's a nice side view of Voodoo's radiator duct. Again, you can see the radically different shape of the inlet and the lower profile. The oil cooler's been eliminated out of the duct like the stock P51 has, and changed to a liquid to oil heat exchanger. And here's a nice shot of the exit door. This is in the open position, I assume, and you can see this closes up to the contours of the fuselage, leaving a very small exit aperture, certainly less than 1/2, maybe as little as 1/3 of the inlet area. So here's a really nice side shot of Voodoo's diffuser. You can see how it gently opens up in area all the way back to the radiators. You can see how thick the radiator is on this aircraft. Of course, you have a lot of pressure available at 450 plus knots. They did a really great job developing this, in my opinion. It follows all the theory really nicely, and obviously it works very well. So here's a good side view photo of the GP5 Sport Class Racer. You'll see the radiator duct is kind of similar in shape to Voodoo. Got the exit door here. In my view, they did a very good job of integrating the radiator into this aircraft, and the aircraft showed some real potential at Reno. So this chart is comparing some of the radiator parameters between my RV6A and Russell Sherwood's Glass Air. And here we've got radiator area. My airplane has quite a bit less horsepower, so it doesn't require as large a radiator as Russell's. So I've got 119 square inches. He's got 240. Rad thickness, my airplane's a little bit slower, so I selected radiator that was somewhat thinner than Russell's. Radiator volume, there's quite a big difference there. He's got a lot more area as well as more thickness. He's got more than double the radiator volume. Inlet area, mine's relatively large compared to Russell's. Again, you don't need as much inlet area when you've got less horsepower. Here's the approximate horsepower of the engines here. And here's one more comparison. Russell has a front cap to go over the radiator to reduce the inlet area for racing, for his sorrel racing. So most of the parameters stay the same here, except the inlet area is reduced from 33 to 24 inches. This chart is comparing a few more of the radiator parameters between my RV6A and Russell's Glass Air. This is inlet area over horsepower. You can see that I've got more inlet area versus horsepower than Russell has. So this is radiator face area versus horsepower. And again, I've got a fair amount less than Russell has. This is rad volume over horsepower. Again, substantially less than what Russell has. Exit area. This is related to horsepower somewhat. Obviously, with less horsepower, I don't need as much exit area theoretically. Russell has a bit more here, but he's got a bit more horsepower. With his race setup, he often can close the exit door up to only 15 square inches of area. This is the expansion ratio, so this is inlet area to rad face area ratio. You can see I've got quite a bit less expansion ratio than Russell has. This is the contraction ratio, so this is the radiator area versus the exit area. Russell's got 10.9 here with the standard setup, and by closing the exit area up somewhat, he can really increase this contraction ratio. And this is inlet area to outlet area ratio. So you can see there's not a big difference between the airplanes here. So here's a chart of duct inlet area versus horsepower versus best climb speed. We've got inlet area in square inches on the left side here, and engine horsepower down below. So you can use this chart to pick the approximate inlet area versus horsepower and climb speed. So if we had a 150 horsepower engine and our best climb speed was 80 knots here, see we should have an inlet area of at least about 32 square inches. So this next chart depicts radiator volume versus horsepower versus best climb speed. We've got radiator volume in cubic inches on the left side here, and engine horsepower down below again, and climb speed here. So again, you can just use this chart. So we've got 300 horsepower, and best climb speed is 120 knots. We can cross that over here, and we'd require about 400 cubic inches of rad volume for that combination. Of course, again, as the climb speed drops off, you need more radiator volume. You don't have the mass flow to dissipate the amount of heat. So with a 300 horsepower engine, and we're only climbing at 80 knots instead of 120, the rad volume would have to go up to about 600 cubic inches here. And I might mention that all these charts are sized on roughly 100 degrees ambient air temperature. So if you're going to be flying in hotter conditions than that, you'll have to have more rad volume, more inlet area as well. If you're flying in cooler temperatures, you can get away with a little less rad volume, inlet area, etc. This chart is mainly concerned with ground cooling. So it's comparing radiator face area versus horsepower versus distance from the propeller to the radiator. We've got radiator face area in square inches over here, engine horsepower down here. And I should mention that we're not too concerned about running at full power here on the ground, but usually the larger the engine, the more horsepower it puts out at idle. And this seems to be the best way to compare these things. What we're seeing here is distance from the propeller. This is 120 inches from the propeller to the radiator, and here is 60, and here is 30. Obviously, as you get further away from the propeller, there's less velocity and pressure available for cooling at the radiator. So this is an approximation. Ground cooling involves many different things, coolant flow, propeller pitch, many different things. This is just to illustrate that the further away you are from the propeller with the radiator face, the more radiator area you're going to need to cool it on the ground at ground idle. This chart is depicting radiator core thickness versus maximum speed. We've got core thickness in inches on the left side, maximum speed in knots down here. And this just gives a range of thicknesses for general aviation aircraft. GA aircraft have to cool on the ground. Obviously, something like a P-51 uses a much thicker rad core than we have depicted here, but they don't cool very well on the ground, certainly not for indefinite periods in hot conditions. And to use this chart, we pick our maximum speed, we'll say 150 knots here, and the minimum radiator thickness we'd want to have is probably 1.5 inches, and the maximum is somewhere around 2.25 inches here. And one final chart for you here. This is a comparison of ground versus flight cooling, and just showing you the factors in play here. So ground idle, only making about 15 horsepower, we'll say on my airplane. The inlet velocity is only about 20 knots from the prop wash. That's about 34 feet per second. And through the aperture in the inlet, that's about 405 CFM. And the available pressure is only a quarter of an inch of water. So in the climb, we've got about 10 times the amount of horsepower, but we've got 4 times the amount of speed, and we've got many times the amount of pressure. So the inlet velocity in feet per second is about 135, and the available flow is quadrupled to about 1600. And in cruise, about 120 horsepower, 140 knots, 236 feet per second. Available flow is up to 2835 CFM. And we don't need anywhere near 2800 CFM to cool it, and that's one of the reasons we have the exit door. We can close that down, reduce the mass flow, reduce the drag through the core. And we've got lots of pressure available from the speed here, approximately 50 times the amount of pressure at the radiator face potentially than we have at ground idle. So we have to take these things into account. The pressure is very low at ground idle, low enough in fact that some of the air won't even penetrate the core. It's very hard to dissipate the heat with such low pressure here. And in high-speed cruise, we've got lots of pressure available and lots of flow available, so we just don't need that much, and that's why we would close the exit door. And the climb is also quite challenging. We've got very high heat and horsepower here. We've got a decent amount of flow, but not so much pressure because the speed is not that high. Remember, dynamic pressure varies as the square of the speed, and that's why there's such a big difference between cruise and the ground idle here, or the climb in fact. Here's a couple more photos of Voodoo's radiator duct, which you might find interesting. And 3 cool photos of the Napier Heston T5, which was designed for world speed record attempts in 1940. Might find this layout pretty interesting and might give you some ideas as well. To sum up a few important points here, the thin radiators are good for ground cooling where you don't have much pressure. Unfortunately, if we have it too thin, we need a lot of area and a lot of volume. That makes for a gigantic radiator which won't fit in your airplane. So we do have to have some depth there. More depth equals more drag generally though, so it's all a compromise. Anyway, I hope you found this all interesting and informative, and maybe you can apply some of the lessons here to your own design. And I just wanted to thank Russell Sherwood for all the information he supplied here, and Mark Cook from Kit Planes as well. That's it for this one. Thanks very much for watching.